Hey, welcome my neighbors. Today we're going to be talking about the ABS sensor tool build. And I have some good news and some bad news. So let's get into it. Just as an overview, in case you're joining us for the first time in this series, what we're designing is an ABS sensor tool, and this was talked about in the last video. This is our overall design. So if you want to know more details about the last video, please go and take a look at that last video on part 1. What talks in depth about this design here. But getting back into this video, the good news about this, we were searching for tools. We were searching for parts to build this this circuit, and the good news is I found 90% of the build. So here it is. This I already opened up is a headlamp, an LED headlamp. I literally got this at a tool store on sale for about $3. So this one, like most of these headlamps, are powered by 3 AAA batteries. And inside the circuit here, 90% of what we need is already here. We got LEDs, we got transistors. I'm going to show you here and bring it closer. And we got a little button switch here. So basically this represents, on our diagram, this part of the circuit already. Okay, the LED lamp, the circuit. All in theory we got to add to it is the transistor, the voltage divider, basically the transistor setup, and the input to the from the sensor. Okay. So what's bad? Well, here comes the bad news. Let's take a dive into how this thing works, and then you will see what the trouble I've been running into. So let's analyze this circuit a bit now that we've broken it open. We need to know how to activate the lamp without using its switch. But in order to do that, we need to look at how the existing switch works. So let's take a look at that in detail. Zoom in even a little further. Okay, so basically what we have here is a switch. The existing switch is on top. When I click it, I hope you can see it. The lamp is lighting up, right? When I click it again, the lamp goes into a dim mode. And when I click it again, it goes into a flasher mode. And then I'll click it one more time, it turns off. So the way this works is that it's this switch here. Let me zoom out for a second. Back into here. This switch here is connected to this integrated circuit here. I don't know what this is. I searched online for the markings on the case. I couldn't find the data sheets for this. But the best way I can explain how this works is it's actually a multifunction controller. Basically, if you see here, there's a 10K resistor here, and this is the this is a p-channel MOSFET, and this is a resistor connected to the LED to control its current. Basically what happens here is the gate of this transistor, of this MOSFET, is connected to this chip over here, and this chip has multiple functions. One, when I click it one time, it can just put this base, the gate, to connect it directly to the ground, and that makes the LED light up at its full brightness, full power. And when I click it again, basically what this chip does is pulses the connection to ground. Now I've measured this. It's about 4,000 hertz. It does a pulse width modulation on this one and connects it to ground. So it switches really quickly, and so what happens is the effect is that the LED is only on a fraction of the time, so it appears dimmer than normal. And then once I click the switch again, this chip switches to a different mode. It has a timer on it and periodically grounds this gate. So what we have to know is, as long as the gate is grounded and there's current flowing through here, that means the lamp will turn on. And that's what we're going to tap into. We have to tap into this gate, and we're going to make our own grounding circuit with the transistor that we're going to add to this. So what is the problem with this circuit? Now, I made a miscalculation, and this is something that I forgot. This is the voltage of the full battery when it's off, the lights are off. You see here on the multimeter it says 4.28 volts. Now, when I switch the lamp on, like this, by pushing the button, you see the light is on. Now if I check the voltage across the terminals, you can see it's 3.8 volts. So again, once again, if I turn it off, check it again, what we have is 4.22. So what's happening here is that it's dropping about I don't know, so 0.4 volts when the light is on, which means it could be a problem in our design. Back in our design, we said that in order to control the gate or the base of this transistor, we're using a voltage divider on the total voltage here to control the voltage at the base, right? Thus to control the current. But as soon as the lamp turns on, if this voltage were to drop at the top here, which it does, because this is a battery powered device, those batteries have its own internal resistance, which is quite high. So it can't supply enough voltage, and it drops, instantly taking the base out with it, right? So when the signal goes high, although the light should be turned on, as soon as the lamp turns on, the total voltage on the power line here drops, and thus the voltage divider would have less voltage out on its output here, and therefore turning this off. So that's a little bit of a contradiction there, right? So we need to find a way to stabilize that voltage, and we're going to get into that. So look what I've rigged up here. This is a poor man's voltage stabilizer. This is basically a series of one resistor and diodes. So the idea is you feed in the input voltage from the red cable here, and what happens is that this resistor provides a voltage drop, and the rest of the other diodes provide a consistent drop of voltage over them. So diodes drop between 0.5 and 0.7 volts, each of them, right? Given a certain amount of current that's flowing through them, right? So we're going to have to experiment with which resistor to use in order to generate the best results. So again, the idea is, if we take the output from here, it's going to be the same. It should be nearly the same, given different input voltage swings, right? So we've measured before, the input voltage swing is about from 4.2 volts to 3.8 volts. So that's a swing of 400 millivolts. Now we have to select the resistor that achieves that creates a better outcome. So basically, when I adjust the voltage on the input voltage and I swing it, the output voltage at this junction right here should not change by that much. Whereas something in the magnitude of 400 millivolts will affect our circuit. Now, if I took the output from here, I'm only getting about 40 millivolts of a swing. So it's much better, much better than the original, and it shouldn't affect our circuit now. So I want to show to you guys what this voltage stabilizer does on my oscilloscope. So basically the yellow line up here indicates I have roughly 4.16 volts, and that yellow line is the source, is the battery voltage. Now if I go to the green line here and I click on that, this green line down here says 2.58 volts. That is the voltage at the stabilized voltage levels. Okay, so it's taking output below that resistor. Now I want to show you what happens when I change the yellow line. I'm gonna fluctuate the source voltage, and you will see that the green line relatively stays the same. So I'm going to lower the voltage now of the yellow line of the source. As you can see, the yellow line comes down to about there. You notice now the green line hasn't changed. Well, we can put the measurement back on the yellow. You can see here, if I drag this line back down, this is my ruler, we're at 380, okay, 3.8 volts. Yet the green line still stays the same, okay, roughly at 2.58 volts. So let's go make it go back up, and you'll see that. So I'll change the supply back up. As you can see, the green line is still where it's hovering where it is, okay. So it's not changing because of the stabilization circuit. Okay, so I can fluctuate it some more. It does move a bit, but the voltage does not swing that much in reality. I'm just playing with it a lot now, right? So if I go lower, down, you see now it's slowly pushing that green fuzzy line down, but it's not moving much. Okay. Before we get too far ahead of ourselves, I've set up the circuit live on the flashlight itself. So I've temporarily soldered the voltage stabilizer onto the circuit, onto the flashlight. I can see here, right? Temporarily soldered onto here, right? And I put the probes on so we can see the voltage change. So here I'm going to turn on the flashlight. So again, the green line is the voltage stabilizer line. The yellow line is the supply voltage. So when I turn on the light now, I'm going to turn it on. As you can see, the yellow line dropped, but the green line fairly much stayed stable. I'm going to turn it off and cycle it through the different modes, and you'll see. Okay, this one. This is the blinking mode. As you can see, when in the blinking mode, you see the light here in the corner here. The supply goes up and down, up and down. Now you can see the green line is actually moving up and down slightly, but it's in the tens of millivolts range. Whereas the supply voltage was moving up in the hundreds of millivolts range. So it's not bad, but it's still not perfect. So here it is. Now I've wired up the voltage stabilizer, again temporarily soldered on, and I also have connected the transistor setup. Now I didn't show the build of the transistor setup because I found one of these old transistors, NPN transistors that I have lying around from previous projects that I didn't use. So I put this one here, I put the right voltage divider here. As you can see here, there's a division here. I just basically squeezed and wrapped these wires together temporarily. I didn't want to solder anything until we can figure out that everything works properly. And with the probes on, I've probed on the green probe. I have on the basically on the base of the transistor here, the PNP transistor that controls the light turning on and off. That's connected to the base, and if I zoom out, the other probe is connected to the gate. The yellow probe is connected to the gate of my transistor that I added, right? So we go zoom in here. So that's on basically the gate is on my transistor is between these two in the voltage divider, just like on the diagram. Now it looks like a mess now, but in fact everything is working as it should be so far. So if I zoom back out, I can tell you on the oscilloscope right now the green is at 4 volts, 4.12 volts, which is basically the supply voltage, and the yellow line is the base, the gate of my transistor that I added. So it's exactly at 1.68 volts, exactly where I want it to be. So that's in the state where no ABS sensor signal is being fed to the system. So that's where it should be. Now what should happen is when the signal is fed to the gate of my transistor, it should add on to the 1.68 volts. So it should add about 0.25 volts onto that, and that should trigger the transistor to turn on, and also thus pull down the PNP transistor that's on the light there. So as soon as that turns on, pulls it down, the light will turn on, and hopefully that'll work. But in the next video, that's we're gonna just leave it for now. But the next video, we're gonna create a test bed. So basically, we're gonna create a alternating current signal and hook it up to the into this light to see if it works. So in order to do that, we're gonna program a microcontroller to generate that signal. Fairly much the same signal as what the ABS sensor will hopefully produce. So if you enjoyed this video, please like and subscribe, and the next one is very exciting. We're going to simulate the signal into this one and see if our setup works. Have a nice day.